Hello viewers, my name is Dr. Ajay from the Department of ECE from Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic about the skyway propagation, some parameters of skyway propagation, critical frequency and the maximum visible frequency. So today's topics are critical frequency, maximum visible frequency and skyway propagation. These are the topics related to antenna space and propagation course. Let us start our session. So let us discuss about the skyway propagation and how the atmospheric layer have been formed in the atmosphere. So here in the year 1925, Sir Edward Appleton showed that the propagation of radio waves at high frequencies is greatly supported by the upper part of the atmosphere of the Earth. So we are going to transmit very high frequencies into the atmosphere, and this atmosphere supports the reflection and refraction to get back the signal to the receiver. So Edward showed that the propagation of radio waves at the high frequencies is greatly supported by the upper part of the atmosphere of the Earth. He also proved that there were several layers of ionization at different heights, and they reflect back the high frequency waves which would have lost into space otherwise. It means that when we transmit the electromagnetic waves from the transmitting antenna, some waves are reflected and some waves are refracted and some waves are escaped into the free space. So this reflection and reflection and refraction concepts takes place in several layers of ionization in the atmosphere. So with the help of number of experiments, the scientist Mr. Edward, he concluded that these several layers show different effect on the radio wave propagation. So there are different layers in the atmosphere. So why these layers are formed, how these layers are formed, and whenever we transmit the electromagnetic rays into these layers, so how the signals are going to reach to the receiver, we will see today about the structure of atmosphere. So we know that the atmosphere consists of mainly three regions. One is the troposphere, the stratosphere and the ionosphere. So troposphere, it is the nearest region to the Earth's surface, about 10 to 20 kilometers. So from the surface of the Earth at a distance of 16 kilometers, we call the layer as a tropospheric layer. So the zone between the 10 kilometers to 20 kilometers above the surface of the Earth, we call the zone as tropospheric zone. The next region of the atmosphere is between the range of 20 kilometers to 70 kilometers of height from the Earth's surface. The last and important region for the long distance communication is from the distance of 70 to 400 kilometers above the surface of the Earth. So the structure of atmosphere is divided into tropospheric, the stratospheric and ionospheric. And in the ionospheric region, there are again some layers are there. So how these layers are formed? So what is the phenomena behind it? What is the distance of propagation when we propagate the signal into these layers? We'll see about the atmosphere. So the atmosphere of the Earth consists mainly three regions such as the troposphere, stratosphere and the ionosphere. And let us see how these different layers are formed in the atmosphere. Let us assume this as the surface of the Earth, and over the surface of the Earth at a distance of 10 kilometers or 20 or 30 kilometers, there are different layers are formed. Here, let us say this is one layer, and this is another layer, and this is another layer. And here this is another layer. So this is the surface of the Earth here. Let us assume here there is sun is there here, and from the sun there are some cosmic rays are falling on this layer. Some amount of cosmic rays are falling here. Let us assume these arrows as cosmic rays on this layer. So you can see in the figure that more number of cosmic rays are falling on the topmost layer of the surface of the Earth. And in the lowest layer, there are more number of atoms. and in the second layer there will be the density of the atoms will be less. See here, you can see here, in the topmost layer, the cosmic rays are falling. The cosmic rays are falling on the over one layer. So these arrows, we call it as cosmic rays, and we are indicated here dots as the atoms. We are indicated as atoms. So there are more number of atoms in the lowest layer. The density is more. The density is less in the next layer. The density is very less in the as the height is increased. As the height is increased, the density is very less. The density of atoms is the density of atoms is very less. So here, whenever the electromagnetic rays, the cosmic rays fall on these atoms, electrons are released. That means the some amount of energy is being absorbed by the atom here. This is, let us assume this is 1, 2, 3 and 4 layer. So whenever the cosmic rays fall over the atom, these electrons, the amount of some amount of energy is being absorbed by the atom, then the electron is released from the atom. So this phenomenon we call it as the ionization phenomena. That means here the ions are found. So whenever the electron is released, these free electrons, we call it as ions. So this ionization phenomena exists here in the first layer. So here, whenever the energy falls on the atom, electrons are released, and these free electrons, we call it as an ions. This total phenomena we call it as a ionization process. So after the first layer, the remaining amount of cosmic rays will fall to the second layer. Will fall on the second layer. So here there are totally 5 atoms are there here. Here there are only 4 atoms in the first layer. Here there are 7 atoms are there in the third layer. Here there are 10 atoms are there. So if there are more number of atoms, it means that the density of the layer is more, right? So here in the second layer there are 5 atoms. The remaining cosmic rays, fall on the first layer. The energy is being absorbed by the number of atoms which are in the first layer, and the remaining amount of cosmic rays energy is going to fall on the second layer. When again the cosmic rays fall on the second layer, again the electrons are released here. Some amount of energy is being absorbed by the atoms here. The electrons are released. Again, these free electrons, we call it as ions. Again, here also the ionization process is repeated here. That means here the ionization density is different. The ionization density is different with respect to the first layer. Similarly, the third layer also, remaining amount of cosmic rays fall on the atoms, and again the electrons are released here. Again the electrons are released, and here the free electrons, we call it as ions. So in every layer, we can observe that ionization phenomena exist. That means the ionization process is going to repeat in every layer. It means that the ionization density will also be different from layer to layer. So the ionization density will also be different from layer 1 to layer 2, and layer 2 to layer 3, and layer 3 to layer 4. We can see here more number of atoms are there in the fourth layer. So here, as more number of atoms are there in the fourth layer, the ionization density will be very high in the fourth layer. The ionization density will be very large in the fourth layer, and the ionization density will be less. The ionization density will be less in the third layer, and as the height is increased, the ionization density becomes very moderate here. And the first layer, the ionization density is very less here. So as the height is increased, we can observe here, as the height is increased, the ionization density value decreases. It means in the lowest layer, the ionization density is more. In the third layer, it is less. In the second layer, it is moderate. In the first layer, the ionization density is very less. So depending upon the value of the ionization density, these layers have been divided into 4 layers in the ionospheric region. One is the D layer. The first layer we call it as This is the D layer. The first layer we call it as a D layer. You can see in the figure. The second layer it is known as a E layer. And the third layer it is known as F1 layer. And the fourth layer is known as F2 layer. So these are the different types of layers which sometimes exist and which sometimes do not exist, these layers. So depending upon the temperature conditions of the atmosphere, some layers will exist during daytime and some layers will not exist during the daytime. Some layers exist during the night times and some layers not exist during the night times. So here when we call it as a D layer, when we call it as a E layer, F1 layer and F2 layer, it depends upon the height. So the D layer exists between the 10 to 50 to 90 kilometers. So 50 to 90 kilometers. The D layer range is 50 to 90 here, and E layer range is 90 to 140 kilometers. 140 kilometers. So 140 to 220 kilometers. It is the F1 layer, and F2 layer is 220 to 250 kilometers. 220 to 250 kilometers. So these are the fixed different layers where the ionization density of these layers will be different. So totally the last and important region for the long distance communication is this is the layer, that is F1 and F2 layers of the long distance, which extends from 70 kilometers to 400 kilometers above the surface of the earth. So yeah, sometimes depending upon the daytime. So during the daytime, F1 layer and F2 layer exist as cosmic rays are going to fall. So during the daytime, this F1 layer and F2 layer and the D layer and E layer are formed here during the daytime. And during the night times, only F1 layer and F2 layer are formed. D layer and E layer do not exist. Why? Because during the night times, the cosmic rays are not going to fall on the D layer and the E layer. So partially over F1 and F2 layers only, some amount of cosmic rays will fall. Hence the ionization process will exist in the F1 layer and F2 layer. Hence, during the daytime, D layer, E layer, F1 layer and F2 layer will exist. And at the same time, during the night times, F1 layer and F2 layer exist, but D and E layer do not exist. So this is about the structure of atmosphere. The structure of atmosphere is divided into three zones. One is the troposphere, stratosphere and ionospheric. And in the ionospheric, we are having the total atmosphere is divided into in the range of 10 to 400 kilometers above the surface of the earth. So this 400 kilometers above the surface of the earth is divided into four layers. One is D layer, E layer, F1 layer and F2 layer. So F1 layer and F2 layer. Seeing in the figure, the ionization is the upper portion of the atmosphere of the earth. It gets heated due to the absorption of large energy radiated by the sun. So large amount of energy falls over the topmost layer. Hence, more number of atoms. The cosmic rays fall on the atoms, but the atoms are very less in the topmost layer. So ionization density value will be very less in the topmost layer of the earth. So here you can see here the height above the Earth's surface, it is 100, 200, 300, 4 meters. So in the month of June, F2 layer and F1 layer exists. In the month of December, F2 layer, the range is 250 kilometers. And a D and E layer, the range is up to 100 kilometers. So what is the skywave propagation? So skywave propagation is nothing but whenever we are going to transmit the electromagnetic waves into the sky, some amount of rays are reflected towards the receiver through one path or multiple paths. So due to the phenomenon of reflection and refraction, whenever these electromagnetics are transmitted to the sky, they reflect back to the receiver from the sky. Hence the name is given as the skywave propagation. So in this skywave propagation, these are the most important parameters we need to find out in the atmosphere. So what is the critical frequency? What is the maximum usable frequency? Least usable frequency? What is the optimum frequency? The vertical height and the skip distance. So these are the things to be discussed in the skywave propagation. So whenever we are going to transmit the signal, at what frequency we need to send the signal. So we need to have an idea about the maximum frequency to be sent from the transmitting antenna. So what is the maximum frequency? At what frequency we send the signal so that it can reach to the receiver, and at that place we need to place the antenna where the signal is going to fall on the surface of the earth. So let us discuss all these topics in the skywave propagation. These we call it as the parameters of skywave propagation. So these are the basic parameters of the skywave propagation. Let us go to the first one, that is the critical frequency. So here the critical frequency for an ionized layer, it is given as the highest frequency at which a wave is reflected back to the surface at vertical incidence. So the critical frequency for an ionized layer is defined as the highest frequency at which the electromagnetic wave is reflected back to the surface of the earth for a vertical incidence. If you observe here, this is the surface of the earth, and we are going to, there is an antenna here, transmitting antenna here, and there is a D layer here. Let us assume this as a D layer. We have taken for our assumption as a D layer, we are going to send the signal towards the D layer. So if this is the antenna, whenever we send the signal directly to the D layer vertically, and this after touching the D layer, so this will reflect back to the surface of the earth like this. Here there is an antenna. So this is the transmitting antenna and this is the receiving antenna. So here what is critical frequency? The frequency at which a wave is transmitted vertically and reflected back to the surface of the earth. So critical frequency is nothing but the maximum frequency at which an electromagnetic wave is and which the electromagnetic wave is reflected to the surface of the earth at particular at vertical incidence. So we call it this as a critical frequency. Critical frequency, it is denoted by the symbol Fc. Critical frequency, it is denoted by the symbol Fc. And we can see here the angle of incidence is 0 here. The angle of incidence, you can see here, this is the angle of incidence. So this is the D layer. So there is no angle here. So we can assume this as theta I is equal to 0. Assume this as theta I is equal to 0. So the signal is going to incident on the D layer with an angle is equal to, angle of incidence is equal to 0 degrees. The critical frequency for ionized layer of the ionosphere is defined as the highest frequency that can be reflected back to the earth by a particular layer for a vertical incidence. So it is denoted by the symbol Fc. So if generally the general equation to determine the critical frequency is Fc is equal to root of 81 into N max. So N max represents the maximum ionization density. Maximum ionization density of a particular layer. The maximum ionization density of the particular layer. So to determine the critical frequency, we need to find out the ionization density of that layer. Suppose if we are going to send the signal to the E layer. So here there is an antenna. This is the transmitting antenna. We are sending the signal directly, vertically to the E layer. So we need the value of N max here. So N max, that is the value of N max is required. We should know the value of maximum ionization density. Then only we can calculate the critical frequency. That is Fc is equal to 9 into root N max. So N max is expressed in cubic meter and critical frequency is expressed in megahertz. So here there is a vertical. There is no any angle of inclination here. So the angle of incidence is taken as 0 here. Theta I is equal to 0. So generally we know that the refractive index, it is the ratio of velocity of propagation of signal in one medium to the other medium. So we call it as a refractive index. So refractive index is given by mu is equal to sin theta I. So mu is equal to sin theta I. So from Snell's law we can write as mu is equal to sin theta I by sin theta R. So we know that the angle of incidence is 0, right? So the angle of incidence is 0 here. So sin 0 is the refractance is given by mu is equal to sin theta I. So for a radio frequency greater than fc to be reflected back to the earth, the condition is given as sin pi I is greater than root of 1 minus 81 n max by f square. So here sin theta I is greater than root of 1 minus 81 n max by f square. And here from this equation we can write fc is equal to root of 81 n max. Root of 81 n max here. So here we can write this as theta I is equal to 0 here. Theta I is equal to 0. Sorry. So fc is given as 9 root n max here. So we know that fc is equal to 9 root n max here. So this we can write as sin pi I is greater than root of 1 minus fc square by f square. So fc is equal to 9 root n max here. So fc square is equal to 81 n max. So sin theta I is greater than root of 1 minus fc square by f square. And we know that the angle of incidence is 0 here. So we will get 0 is equal to 1 minus fc square by f square here. So we will get fc square 1 minus fc square by f square. And if we take minus 1 like this, fc square is equal to f square and fc is equal to f. And what is fc? 9 root n max. So this is the condition sin theta I is greater than root of 1 minus fc by f whole square. So the condition So the critical frequency is given by the equation 9 root n max, and for a radio wave with a frequency greater than fc to be reflected back to the earth, the condition is given as sin theta pi I is greater than root of 1 minus 81 n max by f square. But fc is equal to root of 81 n max, right? So fc is equal to root of 81 n max. So for a height of 70 kilometers for D layer, fc is there are some standard values given for the ionization density, the critical frequency for different heights of the layers. So for the D layer, if the height is, we know that the height of the D layer is 70 kilometers, and n is taken as 400 cubic per centimeter cube, electrons per centimeter cube. And for E layer, fc is equal to 3 to 5 megahertz, n is equal to 5 to 10 power 5 electrons per centimeter cubed, h is equal to 100 kilometers. And for F1 layer, fc is equal to 5 to 7 megahertz, n is equal to 2 into 10 power 6 electrons per centimeter cubed at a height of 180 kilometers. And for a height is equal to 325 kilometers from the surface of the earth, F2 layer, the critical frequency is 10 megahertz, and capital N is equal to the electronic density, ionization density is given as 2 into 10 power 6 electrons per centimeter cubed. So 2 into 10 power 6 electrons per centimeter cube. So critical frequency equation is fc is equal to 9 root n max. And also the theta, that is sin pi I, is greater than root of 1 minus fc by f whole square. So this is about the critical frequency, that is the highest frequency at which a wave is returned to the surface of the earth at vertical incidence. If we call it as a critical frequency, denoted by the symbol fc. So we know that mu is equal to sin pi I by sin pi r. This is Snell's law. This is root of 1 minus 81 n by f square. So for critical frequency, we can write pi I is 0. So 0 is equal to root of 1 minus 81 n max by f square. So 1 minus 81 n max by f square is equal to 0, and this is equal to minus 81 n max by f square is equal to 1 minus 1, and minus 1 is get cancelled. So f square is equal to 81 n max. So 81 n max is nothing but fc square. So fc is equal to f. So here the maximum visible frequency is defined as the highest frequency at which a wave is returned to the earth. The maximum frequency at which a wave is returned to the earth for a given distance of propagation. For a given distance of propagation between the 2 points. Suppose let us say there is a transmitting antenna here. Here there is a transmitting antenna, and here there is a receiving antenna. So we are going to transmit the signal at 5 megahertz. At 5 megahertz, when we transmit the signal is going to touch any layer here. There is a D layer here. It is going to touch here. It is going to fall at up to this distance, 1. Let us say 1. Now I am going to increase the frequency to 10 megahertz. I am going to increase the frequency to 10 megahertz. If I increase the frequency, the signal is going to go to the topmost layer, that is the E layer. Again, it is going to reach to the second point here. And let us increase the frequency to 15 megahertz. Let us increase the frequency to 15 megahertz. When the signal is going to the topmost layer, it is going to reach to the receiving antenna. That means at 15 megahertz is the maximum frequency where the wave is returned to the receiving antenna for a given distance of propagation. The distance is fixed here. The distance is fixed. That means let us say 10 kilometers. The distance between the transmitting antenna and the receiving antenna is 10 kilometers. So at what frequency we need to send the signal so that it reaches to the receiving antenna. It reaches to the receiving antenna. So we call it as the MUF, that is the maximum usable frequency. So the maximum usable frequency is defined as the maximum frequency that can be used for the skywave propagation for specific distance between 2 points. For specific distance between 2 points on the earth. The highest frequency for skywave communication for each point on the globe, the value of f MUF will be different. So here, for every layer, the MUF value will be different. The maximum usable frequency value will be different for every point on the globe. The value of MUF ranges between the 8 MHz to 36 MHz. The maximum usable frequency that we use for between the transmitting and the receiving antenna between any layers, it ranges between 8 MHz to 36 MHz. But due to the solar activities, the higher limit may even extend to 50 MHz. So up to 50 MHz also we can transmit the signal so that the wave is returned to the exactly the receiving point for the given distance of propagation. Now let us derive the expression for MUF. So here, whenever we transmit the signal here, let us assume mu is equal to sin pi I by sin r. We know that the refractance is given as a mu is equal to sin pi I by sin pi r. That is equal to root of 1 minus 81 n by f square. So the angle of reflection is here, we are assuming as 90 here. The angle of reflection is 90 here. So the maximum usable frequency occurs at not greater than 90 degrees. So here, if you see here, this is the D layer, and this is the transmitting antenna, and this is the receiving antenna. The distance is 10 kilometers. The distance is, so let us say 10 kilometers. Here we are going to transmit the signal, and it is going to reach to the receiver. So this is known as the MUF. That is the maximum frequency we are going to send from the transmitting antenna. And this is going to touch any layer. It may be D layer or E layer, and the wave is returned exactly to the receiving antenna at a particular frequency for a given distance of propagation. So here, the angle of reflection is not greater than 90 degrees. The angle is not greater than 90 degrees. That angle only, the wave is going to return to that angle only. The wave is going to return to the receiving antenna. The wave is going to the receiving antenna. So here the pi r, that is the reflection angle, is taken as 90 degrees only. Beyond that, the signal is not going to return to the receiving antenna. Beyond that, we cannot send the signal to the receiving antenna. The maximum angle of reflection will be only 90 only. So under this condition, we are going to place here pi r as the value of 90. So sin 90 becomes 1 here. So sin 90 is equal to 1, we'll get sin pi I is equal to root of 1 minus 81 n by f square. So based upon this condition, we'll get sin pi I by 90 is equal to sin 90 is equal to root of 1 minus 81 n max by f square of. So this is the f we have modified as f is modified as f square of here, and here this is sin 90 is equal to 1. So we'll get sin pi I by 1 is equal to sin pi I. So sin pi I is equal to root of 1 minus 81 n max by f square of. So squaring on both sides, we'll get sin square pi I is equal to 1 minus 81 n max by f square of. So from this expression, we need to find out the value of f mod. So from this expression, we need to find out the value of f square mod. But we know that fc square is equal to 9 n max, 81 n max. fc square is equal to 81 n max. So we can substitute this value here. So you will get sin square theta I is equal to 1 minus fc square by f square mod. So let us substitute here sin square theta I. We shall take the sin square I theta I to the right hand side. You will get fc square by f square mod is equal to cos square theta I. So f square from this equation will get f mod is equal to fc secant theta I. So f mod is equal to fc secant theta I. So this is known as the maximum amount of frequency at which a wave is returned to the earth for a given distance of propagation, and this is also known as the secant law. So here f mod is equal to fc into secant theta. You can see here, so 81 n max by f square mod is equal to 1 minus sin square pi I, and here 81 n max by f square mod is equal to cos square pi I, and fc square is equal to 81 n max. So we are going to substitute this value here, 81 n max. So we will get fc square by f square mod is equal to cos square theta I. So from this equation, you will get f mod value. From this equation, you can directly get the value of f mod. That is equal to f mod is equal to fc square, fc by cos theta I. So this is equal to fc secant theta I. So f mod is equal to secant pi I into fc. So from the above equation, it is clear that the value of maximum usable frequency f mod is always greater than the critical frequency. So f mod is greater than the critical frequency of the layer by the factor secant pi A. So f mod is greater than the critical frequency by a factor secant theta I. So this is also called as a secant law, and it indicates the highest frequency to be used for the skywave propagation between the 2 points on the earth for a given angle of incidence. So it also indicates the highest frequency to be used for the skywave propagation between the 2 points on the earth for a given angle of incidence. That is theta I. Now let us derive an expression, the Muff equation for the flat earth. So let us find out the maximum usable frequency for flat earth. So let us assume the distance between the transmitting antenna and the receiving antenna is 400 kilometers. So at a far distance, we are going to assume the earth is not curved. So earth is assumed to be the flat. So let us assume the d as the distance, capital D as the distance between the transmitting antenna to the receiving antenna, and h is the height of the layer h. We are denoting as h here. And Ln represents the distance here. The total distance is taken as d here. And O is represented as the midpoint of L and N. So O is represented as the midpoint of L and N here. And here d by 2 and d by 2. The distance is d by 2 or d by 2. And let us assume that the transmitting signal is going to touch the wave, touch the point M in the atmospheric layer with an angle of incidence pi I, and the angle of reflection is pi R. So these are the assumptions which we are going to discuss in our derivation. So L, M, N, it is the path where we are going to transmit the signal from L to N, and M, it is one of the points in the atmospheric layer where it touches and reflects. The wave is going to reflect back. So from the figure we can write as LO is equal to ON is equal to d by 2 and MO is equal to h. This is the height here, and from the Pythagoras theorem, we can write OLM from this triangle OLM, we can write here LM square is equal to D by 2 whole square plus H square. So Lm square is equal to D by 2 whole square plus H square. So similarly for this triangle also we can write here Mn square. Mn square is equal to D by 2 whole square plus H square. So we can write Lm is equal to Mn. So Lm is equal to Mn is equal to square root of D by 2 whole square plus H square. So square root of D by 2 whole square plus H square from the figure. And from the figure we can write cos pi I is equal to MO by LM. So adjacent side to theta, cos pi I is equal to MO, that is MO path by the adjacent by hypotenuse. This is the hypotenuse. So MO by LM. So MO, it is nothing but the height. MO, it is nothing but the, here it is the height here. This is the D by 2 and this is the D by 2. And this is the L, this is O, this is M and this is N and this is pi I. So cos pi I can be written as MO by LM. So MO is nothing but the height from the surface to the layer. So h by root of D by 2 whole square plus H square. So simplifying we get 2h by root of D square plus 4h square. So the maximum visible frequency, we know that the angle of reflection is 90 degrees. The angle of reflection is 90 degrees. So we know that we have derived an expression, the mu is equal to root of 1 minus 81 n by f square. We have also derived the expression for f mof earlier, that is f mof is equal to, this is the equation, f mof is equal to 81 n max by cos square theta I. So you will get here f mof is the secant law, that is f mof is equal to fc by cos theta I. So earlier we have discussed that f mof is equal to fc secant theta I. This is the secant law. So we are going to take this expression to derive the expression for f mof for flat earth. So here f mof is equal to fc by cos theta I. So we have derived the expression for cos theta I, that is 2h by root of square root of d square plus 4h square. So from this expression, if you cross multiply and simplify, you will get f mof is equal to fc into root of d square plus 4h square by 2h. We shall split this 2h for the numerator and denominator here separately. If we split, you will get f mof is equal to fc into square root of d by 2h whole square plus 1. So f mof is equal to fc into square root of d by 2h whole square plus 1. So this is the derivation for the expression of f mof for flat earth. So we have seen here, just we have taken the triangle here, L, M and N. We have identified the height as h here. So this is the d value, this is d by 2 and this is d by 2 and this is pi I and this is pi r. So we know that from this we are going to find out the cos pi I value. So cos pi I is nothing but h, cos pi is angle of incidence by Lm here. Angle of incidence adjacent side to theta by hypotenuse, h by Lm. So we need to find out the value of Lm. We need to find out the value of Lm. So Lm is nothing but, it is square root of d by 2 whole square plus h square. So if we substitute this here and if we simplify, you will get f mof is equal to fc into square root of d by 2h whole square plus 1. So just we need to find out the value of Lm and substitute the value of the cos m in this secant law, that is f mof is the secant law, that is f mof is equal to fc into by cos theta I. So if you substitute this cos theta I here, you will get fc into square root of d by 2h whole square plus 1. So this is the these are the concepts we have discussed today. So let us have a recap. We have discussed about the skyway propagation, the structure of atmosphere, how the layers are formed, and what are the parameters of the skyway propagation. That is the critical frequency and what is the maximum visible frequency. So the difference between the critical frequency and the maximum visible frequency is that the maximum frequency at which a wave is returned to the earth at vertical incidence, we call it as a critical frequency, and the highest frequency at which a wave is returned reflected back to the surface of the earth for given distance of propagation, we call it as the maximum visible frequency. So there are two derivations. One is the derivation for flat earth to determine the value of maximum visible frequency. So f mof is given by fc into square root of d by 2h whole square plus 1. Let us discuss the MUF value, that is the maximum frequency for a curved earth, in the next session. So for references, you can refer these textbooks, that is the Antennas and Wave Propagation by Bakshi, or you can also refer the K.D. Prasad, or you can also refer the textbook Balanis. So these are the textbooks to be referred for these topics. One is Balanis, second one is Bakshi, and the third one is the K.D. Prasad, the Antennas and Wave Propagation. Let us close our session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.